Hi everybody, Mr. Slomka here. We're going to talk about 12.4 Day 2 today. It's still infinite limits and still limits of sequences. We're going to talk about some of the old things that we did last time. We're going to look at some of the old problems as well, but we're going to try and drive a couple facts home to get these to be a little bit easier, and then we'll look at those problems and maybe approach them in a little bit of a different way. So right up here at the top, what we have is we've got a couple rules for the road that are going to really help you out when you're trying to work on some of these problems. Last time when we talked about 12.4 Day 1, you might have noticed that all the things we were taking limits of were fractions. They were rationals. And so what we have is we've got some special rules here for rationals that we're going to follow. All of these rules have to do with the degree of the numerator and the degree of the denominator. The numerator is going to be represented by n of x, n for numerator, and our denominator is going to be represented by d of x, d for denominator. Degree is that high power. So here's our first rule. If the degree of the numerator is less than the degree of the denominator, top is small, bottom is big, then the limit of that fraction n of x over d of x as x approaches infinity is going to be 0 every single time. That's a really, really nice, easy thing to write down. You can just move on with your life, which is great. We got a couple of those last time. We'll maybe get some more today. Next one, if n of x is equal to d of x, so the degree of the numerator and the degree of the denominator are the exact same, then this is actually the long cut. What you have to do is you have to take the limit of the numerator and you have to take the limit of the denominator and then kind of put them all together. This means you basically have to do it the same way we did last time. Last one. This is another one that we've seen before. If the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. So basically what we're talking about when the top is bigger than the bottom is we're talking about an improper fraction. We've seen improper fractions before and they cause us lots of problems when we were like partial fraction decompositioning, but this is just back again. Improper fractions are temperamental, they have some issues, so we have to always kind of watch out for them, and this is another situation where that's going to happen. So that is our rules. We're going to be looking for these situations and maybe we can jump to some nice fast answers, and then sometimes maybe we'll have to do a little bit extra work. But these are cool things you can use and to speed up the process. Also, another thing to point out is just this wording on converge and diverge. If you have these limits and they're heading off towards infinity and you can actually get an answer like 0 or any other kind of number, then it is said to converge at that number. If you get a limit does not exist situation, then that is the one that is said to diverge. That's the big word right there. Okay, let's try to take a couple looks at some of these ones down here. Now, these ones are sequence problems, and because they're sequence problems, what you have to do is you're given a problem that does not start with limit, and you actually have to create the limit. And we're looking for the last term in the sequence, so we're looking for the infinite term of the sequence, so we're doing the limit as n approaches infinity. So what I'm going to do today, rather than going about it the same way I went before, I'm going to compare some degrees. Degree for the numerator is not written, but it's a 1, and the degree for the denominator is also not written, and it's a 1. Those are the exact same degree on top and on bottom, which means that I am talking about option 2 right here, which is the longest option. And that means that I am going to have to basically do it the same way I did last time we talked. So that means I'm going to have my 4n plus 5 in my numerator, and I'm still going to have my n minus 1 in my denominator, and I'm going to divide everything by that high degree from the denominator, which is n. So that guy gets divided by n, and everything else gets divided by n. We get some canceling happening here for some of your first terms, which is great, but not all of them, and that's okay too. And that's going to leave you with a 4 and a 1, which is great. And then over here, your 5 over n is going to stay 5 over n, and your negative 1 over n is also going to stay negative 1 over n. We can't really plug an infinity in, but we can talk about the concept of what happens when we would possibly do that. Constant terms are going to stay the same, so our 4 is going to stay and our 1 is going to stay. If a very large number went in here into the denominator, it would cut that 5 up into so many pieces that you wouldn't even be able to see them because it'd be so small. The whole thing is heading towards 0. Same thing down here. The big denominator is going to turn that whole thing into basically a 0. So we're going to end up with this. And we can simplify that down to just 4 over 1 or just 4. There you go. So we basically took the derivative, or the limit of the numerator and the limit of the denominator separately, and then we got our answer there. So it wasn't very fast, but it did work the exact same way it worked before. Let's take a look at another one. So now this one, if you take a look, we've got n, which has a degree of 1, and n squared that has a degree of 2. So if you're interested in a limit as n is approaching infinity of 4n plus 5 and n squared minus 1, well, once again, numerator is less than denominator. So if you go up here for our less than case, that means that the limit is going to be 0. And that was so fast. We're done. That's, as soon as you know that the numerator is less than the denominator, you can write down 0 every single time. If you don't believe me, if you're not convinced, there's a couple things you could do. First of all, a nice easy one would be to graph it. So if you want to graph that guy, here is the equation right there. It's all typed in, and then we can graph that and take a look. If you take a look, you'll see that the asymptote is right there on the x-axis, and your graph is coming down, 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 closer and closer and closer, but not going to actually get to that asymptote until you reach infinity. The other thing you can do is you can go back and look at the 12.4 day 1 lesson, and you'll see the slower way that I had done this problem and see that you do actually get 0 in that version as well. So that is nice. Last one right here, and then once again another problem from section 12.4 day 1. Once again, what you have is you've got a power of 2 and a power of 2, which means that you have to do it the slow way. So as I'm working on this one, something I want you to notice. A lot of people are like, cool, shortcut, that's awesome. I love shortcuts. Thank you, Mr. Slomka, for the shortcut. Be sure to write it on the formula sheet for me so I can use it. Well, I'm not going to. I'm not going to write it on the formula sheet for you to remember. Or for me to remember it for you. So if you want to use a shortcut, you got to have to embed it into your brain. And for some people, that's really, really easy. I was never one of those people. So you know what? I would usually just typically go back and do the problems the exact same way that we had done them in the day 1 lesson. And that's great. I mean, it works. It's not particularly long or difficult. You end up with some very good answers, and it works out really, really nicely. But if you are one of those people who's like, oh, I have this great trick, I can use my trick to help me remember this shortcut, and then I'll be good to go, then awesome. Good for you. I'm proud of you. I just want to provide you with this opportunity. So there you go. There's your answer for that guy right there. And once again, I had to do it the slow way. I usually just end up doing them all the slow way because I don't trust myself to remember the trick. Okay, backside. This is where things get a little bit more exciting. So we had talked about this problem specifically last time, and I want to talk about one that's a little bit bigger and uglier as well, and I'm going to use the same kind of concept, and we're going to use this degree really, really to help us out. So for this one right here, it's another sequence one, so we're going to try and set it up as a limit as n is approaching infinity. And here's the thing. We're interested in the degree, which is the highest possible power. So what I'm going to do is when I approach this problem, I'm going to just be focusing on the biggest powers that I can for the numerator and for the denominator. So over here for the numerator, n times n is going to be n squared, times another n is going to be 2n cubed, and then times 5 is I'm going to end up with 10n cubed. Now there are other terms, and you can FOIL it all out to find them, but for right now I am only interested in the degree. Same thing for the denominator. Down here, n cubed times 6, that's going to give me 6n cubed down there as well. So up here there are other terms, but I'm too lazy to write them down. Down here as best I can. So if I'm comparing degrees now, I get equals. They're both the exact same thing, which is n cubed. That's not a bad thing, though. That just means you have to go through it the same way that we did before. It's not going to make your life longer. It just doesn't happen to make it any shorter. So I'm going to do this the same way that I did last time, and I think this is kind of cool. What's going to happen here is that because of this n cubed down here, I need to divide everything by n cubed. So I'm going to do that for sure. But you have to think about what exactly is happening here because there's terms that I haven't written down, and that is actually okay. So down here in the denominator, I'm going to divide by n cubed, and that's going to work out really nicely. And up here in the numerator, all of these terms are going to get divided by n cubes as well. So I should technically have a couple of them. Well, for my first term, that one's going to have a couple n cubes, and they're going to drop out, which is going to leave me with just the 10. All the other terms that I did not write down, they're going to have a power that's lower than a cube. I don't exactly know what it is, but I do know it's going to be lower than cube. I could figure that out really easily, but I'm just going to stick to the hypothetical here. Because they're all lower than a cube, that means that the n in the denominator is always going to stay, and that means that you'll always end up going to 0. So it really isn't going to help you or hurt you in any way if you don't know what those terms are. So these are the only ones that really kind of matter, because these are just going to turn into some big fat zeros after a while. So that means that this 10 and that 6 are the real influential pieces, and everything else just pretty much falls to the wayside. So we can end up with a nice limit by just focusing on those first two terms, and that can be reduced, and it's going to reduce down to 5 over 3. Same thing for this guy right over here. Let's take a look at this one. So if I'm looking at that guy, once again, I want to set it up as a limit as n approaches infinity, and I want to look at some of these high powers. So in my numerator, n squared times n is going to be n cubed, times another n is going to be n to the 4th. Now there's an 8n over here, which might tempt you to bring it up to n to the 5th, but that's not going to happen because you have a plus sign here, so you don't multiply by that. So you have n to the 4th, or specifically 4n to the 4th, showing up in here. Now you do have a 13 out there, so if you want to be really kind of specific. What you're really talking about there is 13 times 4 n to the fourth, or 52 n to the fourth. Now we will have a bunch of other terms, including that 8n back there, but I don't really care what they are for right now. I'm just going to hold off. Down here in the denominator, this n to the eighth is going to get distributed to both of those terms. So our biggest one that we're going to have is negative 6n to the eighth. Or sorry, to the ninth, I should say, because we already had an n right there. So we have an n to the eighth and one more n, which is going to bring us up to n to the ninth. So now to compare degrees, I have a power of 4 and a power of 9. Very easy to tell. Denominator is bigger. Numerator is less than denominator. We had a good rule about that. When the numerator is less than the denominator, we had this really nice answer that shows up every single time. The answer is 0. So for this one, I really don't have to do any more work than that. As soon as I know that I've got that small power in the numerator and that big power in the denominator, I know that my answer is going to be 0, and it works out really great. So that shortcut is valuable, and it's awesome, and so you should try to hold on to it. There are 3 things written here. If I was going to hold on to one, I'd probably try to hold on to that top one. I think that one would be the one that I would really want to hold on to. This bottom one, if you think about it logically, you might be able to hold on to that one as well, but that top one is the main one that's going to help you out. That's the best shortcut that I have for you today. Alright, down here at the bottom, story problem. We haven't had a story problem in a while, so I wanted to give you a story problem. And this one's a cool one. So it says, you're manufacturing greeting cards. It costs 65 cents per card to produce, so that would be like ink and paper. So like the raw goods that you need in order to produce these greeting cards. You also have this initial investment of $4,500, which is used to set up the business and buy those printers. Write an equation that represents the cost associated with producing X cards. So we are going to be talking about how much things cost us today, and our costs are based off of 2 things. So we have our 65 cents that we're going to be spending, and that we're going to spend that a lot of times. Every time we make a card, we're going to spend the 65 cents. So it's going to be multiplied by X. The $4,500, however, was a one-time deal. You spend that money, you already have your printers, you have your building, and now you don't have to worry about those things again. It's not like you have to buy printers every time you walk through the front door. So we've got our 2 pieces right here, one with a variable and one without. So then what happens a lot of times, especially if you're making greeting cards, you got to think in the long-term game. I'm not interested in making 10 greeting cards or 100 greeting cards. I want to know what's going to happen when I make my millionth greeting card or my trillionth greeting card, because that's usually when the profits start to kick in. You have to patiently wait until you've created this big, massive collection, and people are coming to you all the time for greeting cards all around the world. So what we're going to look at now is we're going to look at something called average cost. This is a same capital letter C I have, but now it's got a bar over the top of it, and that is in fact called a bar. C bar right there. Here's how it works. It's going to be your cost, but it's going to be over the number of cards that you create. And so what this is like the average cost per card. We have 2 different costs that are going together, but we're going to kind of combine them together to make one average cost. So for my formula, what that's going to be from C bar, specifically for me, is that's my 65 cents times X cards, that part stays the same, and my $4,500, which was my initial startup fee, and then it's over the number of cards that I'm creating. Well, I don't really know exactly how many, so it's going to be over X. There you go. Alright, so then the next part, what I want to do now is I want to find out about the average cost for a couple different places. What if I made 5,000 cards? Then what would be like the average cost for each of those cards? Well, what I would do is I would put the 5,000 in here and in here. So I would plug it in 2 spots. When you do that, if you calculate with the 5,000 here and another one here, you're going to end up with $1.55. Basically what this is doing is that's saying that you have to pay your 65 cents per each card, and then it's taking the $4,500 right here and splitting it up over the 5,000 cards. If you split up that $4,500 over the 5,000 cards, you end up with each card costing about $1.55. So if you're only going to make 5,000 cards, you should charge more than $1.55, probably like double. What if you made 50,000 cards? Well, if you make 50,000 cards, that means you're going to be dividing by something that is a lot bigger, and that means that your average cost goes down. Now it's only 74 cents. So that means that this $4,500 has been spread out over more cards, and so each cost for each card goes down. And so now if you charge like $3 for your cards, now you're making a lot more profit, which is great. And people are very, very happy to pay $3 for a greeting card, so you're going to make a lot of money. They'll be happy with your product and everything will be great. Okay, let's keep going. So now what if we make 500,000 cards? Now what we're down to is we are down to 66 cents. And I actually had to round up. That was actually 65.9, and I rounded up to 66 cents. So if you look closely here, we're getting pretty close to actually just the raw cost of creating the greeting card. You'll always have to pay for that paper, you'll always have to pay for the ink, but all of a sudden your building costs and your printer costs that you paid right away, they're just kind of melting away. It's been spread out so evenly over so many cards that it's just kind of going away. So now a lot of businesses, what they're interested in is they want to keep going. They're greedy, they just want to keep on making more and more and more, they want to be more successful, keep growing their business. So something they're interested in is like, what about the infinite card? What if I just keep going forever and ever and ever? I pass it off to my kids and their grandkids and all that kind of stuff. So what we're going to do now is we're going to talk about the limit. What would happen if we take the limit of our cost function, or average cost function, I should say, as we get towards our infinite card. Now, it would be impossible to type an infinity into this problem, so we're not going to. We're going to approach infinity by using a limit. And this is very doable. You would not have been able to use just an infinity on its own. But because we're using a limit, it's going to work out great. So first of all, because today is today and we learned our cool tricks, it would be good to consult our degree. Degree for the numerator is 1, degree for the denominator is 1. No shortcut for us today, and not for this problem. So we're going to do it the long way, where we divide everything by that high degree from the denominator, which is x. And when you do that, some of your x's cancel out, which is really, really nice. And you're left with the limit as x approaches infinity, and you have your 0.65 in the numerator. You've got your 4,500 over x in the numerator, and down the denominator you just have a 1. Well, if the infinities start showing up specifically in that one spot right there, what's going to end up happening is that whole thing's going to turn into a big 0. So we're going to end up with 0.65 over 1, or just 0.65. On your infinite card, when you've sold infinity many cards, what happens is that initial cost for setting up your printers and your building is now basically gone. It is no longer really affecting your profits or your costs, and so you are just down to paying 65 cents a card, which is really, really great. And that's what most people are trying to work their way towards. They want to buy these things, they want to really get their money out of them, so they're just going to run them and run them and run them until basically they've paid for themselves and then kept going after that. And so what we've done is we've done this really cool thing. This is an awesome problem, really, really great. Definitely a good business analysis that you can use your limits for, something other than just basic pure calculus. So I'm excited about that. We'll talk more about section 12.5, but a little bit later. Good luck on your AP exams. Come talk to me in class if you have any questions.